speaker is Katzarkov from Miami. He will talk HMS and application.
So, thank you very much for inviting me to speak here. Congratulations on the program. So, I was planning to talk about something else, so I didn't even have time to change the title. But Mark decided to organize an exam. How much did we understand the Pranab and Thailand from this morning lecture? So we scrambled over lunch, and so I'll try to tell some story about this. So, still, I need to connect the discussion with something that I was planning to talk about, namely about some applications. So let me recall briefly a classical story. So as I mentioned before, something like 30 years ago, Donaldson was trying to find a counterexample to something that is called H-cobordism conjecture, namely examples of four-dimensional smooth manifolds, which are homeomorphic by Friedman's theorem. That means that take care. By Friedman's theorem means that quadratic forms on H2 are isomorphic, and so introducing so-called Donaldson polynomial invariant, Donaldson was able to show that we can find examples of such a smooth manifolds, which are homeomorphic but not diffeomorphic. And the first example is a so-called Dolgachov surface. So the Dolgachov surface is a surface which is of the class of elliptic surfaces, and it's obtained geometrically in the following way. So you take the two elliptic curves, you plot the points in which these elliptic curves intersect, and then after that you perform two log transforms over the two of the smooth fibers of the rational elliptic vibration you get by blowing up these 9 points. And so the algebraic surface that you get is not known to be describable as a surface obtained by a geometric construction. But what Donaldson proved is that its Donaldson invariants are different from the one of 62 blown up at 9 points. And the reason for that is that the surface being of the elliptic type has very few basic classes. So I won't have time probably to talk about the definition of basic class today, since the talk has changed a little bit. But so what Donaldson was able to do is use the fact that one of the surfaces, namely the Dolgachov surface, is not rational, and connect this with lack of basic classes, and as a result of that, show that Donaldson polynomial invariants for Dolgachov surfaces are different from the one of the rational surface. So the goal which we'll try to pursue in this talk is to set up some ground for investigating categorical Donaldson invariants, and eventually talk about the connection of these invariants with questions of rationality. So one of the main issues that will come is that in the language of categories there is a notion of semi-orthogonal decomposition, which is not variational invariant, but certainly we will try to measure this semi-orthogonal decomposition by introducing some categorical Donaldson invariants and hopefully get something that is variational invariant in such a way. So, similarly, a little bit after Donaldson example of the Dolgachov surface, Kochik studied a different type of surface, so-called barrel surface, and he proved that Donaldson invariants for this barrel surface are different from the Donaldson invariants of P2 blown up at 8 points, which happen to be homeomorphic to this surface, barrel surface, surface of general type. So barrel surface is a little bit easier to realize geometrically than the Dolgachov surface. So classically, in four-dimensional topology, the main procedures of creating interesting examples, and certainly these two examples which I have mentioned can be explained in such a way, is the procedure of rational blow down. Namely, we have a sequence of spheres with self-intersections minus p plus 2, minus 2, minus 2, minus 2, and intersecting UI, these spheres intersecting in 1. And so you take this neighborhood of this configuration of spheres, you blow down, and like you cut it out, and instead of it you put another configuration of spheres with different intersection numbers. So this is a main procedure of constructing interesting examples, and a lot of mileage was done by many people in studying how Donaldson invariants change under this procedure. And so I'll certainly at the end of the talk propose a categorical analog of this observation. So one of the main application of Donaldson theory is that so there are some four-dimensional manifolds which are called manifolds of simple type. So I won't go into the definition. And Donaldson invariants tell you that these four-dimensional manifolds, let's say they are symplectic, minimal, with B2 plus greater or equal to 1, cannot be split as a topological sum over some Riemann surface as two manifolds of simple type logically connected over a Riemann surface, both of them minimal with B2 plus greater or equal to 1. And so this impossibility to split four-dimensional manifolds had rather amusing consequences in the classification of four-dimensional manifolds. So I'll try to propose some categorical version of that. And so the main example in constructing many interesting examples in four-dimensional topology is this elliptic surfaces which are obtained from the elliptic surface, rational elliptic surface P2 blown up in 9 points with the procedure of surgeries or rational blow down. So at the end of the talk, I'll propose a categorical analog of this procedure. So, of course, I must say that already some categorical steps were made in this direction. So the first one was that these two surfaces, Barlow surface and the Dolgachov surface, they actually have a peculiar behavior when it comes to categories. they have semi-orthogonal decompositions, and in these semi-orthogonal decompositions, you have some peculiar categories appearing. So these are categories with trivial K theories, but by themselves being non-trivial. And so such categories are called phantoms. So the phantoms in the barrel surface was computed some time ago by Christian Döning, von Beltmer, and Paul Sosna, and I think that Jacques Jamal computed the example of the Gorbachev surface. All right, so this is the direction we want to move. So the next step will be setting up some ground for exploring this direction. And this will be based on developing what Maxim suggested this morning. So let me remind you that there is this classical GAT theory of obtaining modular spaces. So you have a symplectic manifold X with a group action, the group that has there is G. And the classical GAT enhances this space with a group action with the GAT quotient using Malford stability. So the categorical analog of this will be a non-commutative space, or if you like, smooth and proper category chi, which is K linear, where K is either the field of complex numbers or some non-Euclidean field. And analog of this Malford stability will be the Bridgeland stability, which Max has discussed already this morning. So what I'm trying to do now is to build an analogy between what Max has explained this morning and the classical story that we all know. And so if I have some unitary group, K, then I can actually consider the quotient of the action of K with respect to a subgroup of G. And then on the categorical side, the analog of this will be a OK, where O of K is the ring of integers, linear category, which will denote this category appeared this morning in Max's consideration, which will denote by chi 0, and the property of chi 0 is that when tensor with O of K, it's we get back our initial non-commutative space of like our initial K linear category chi. So classically, we have this moment map associated with the algebra K to say infinity functions over X. And then the analog of this is what we all know as a central charge.
But why is this analog? Why? What's the motivation?
Well, the motivation is going to be clear on the next page. So what we want to do is to build a categorical analog of the 50 years old theorem, which is called the theorem of Narasimhan and Sheshadri, that you have a correspondence between the Bridgeland stable objects and certain Hermitian Einstein objects on the category. So the motivation is that we come down here into this Kobayashi-Hitchin correspondence, which we classically know. We correspond to Kobayashi-Hitchin correspondence for these modular spaces. One being the modular spaces of the Hermitian Einstein objects in the category, and then being just the other part of the corresponding being the modular space of Bridgeland polystable objects. That's the motivation this is the idea that we are trying to pursue. And of course, if this is eventually done, that would hopefully allow us to come up with a nice intersection theory on these modular spaces by building analogies further. So we take the inverse of the moment map, and so it's the classical construction, but for the categorical one, this is a category of Hermite-Einstein object in chi0, and so and of course the main part of the discussion will be to say properly what this is. So classically we have this negative flow that allows us to eventually define the corresponding Kempf's theorem, and so the categorically we want to build a flow on the modular space of metrized objects, something that Max has introduced this morning. These are objects with emission metric on them, and then using the flow we are going to try to say what are these Hermite-Einstein objects with respect to this flow. Namely, we will use a certain Carrier potential by analogy with the Kempf-Ness function in the classical theory to say that, all right, so these Hermite-Einstein objects are the critical points of this Carrier potential, and that will be the way to complete this correspondence. So this is just basically the goal, trying to build this analogy. I'm not, once again, there are no definitions here, and probably there won't be that many precise definitions today, although I'll try to give some, and then we'll consider one example. This is the example that Maxim actually started discussing today, example of quiver. So any question?
Too many questions.
So basic example. We'll now.
Yeah. So
Next slide is basic example.
no, not yet. So all right. So first we will start with the definitions, and then we'll give the example. So once again, this was just outlining the idea. So let's start with the following definition. So we'll call the following data Kobayashi teaching data on a non-commutative space, it's not proper category chi. And so this are the following 6 type of data. So first is Z, so the group homomorphism, which we all call central charge, from the K0 of this category to the complex numbers. Then the second is MET. This is the space of metrized objects. These are objects with Hermitian metrics on them. So the third is this S data. This is the Carrier potential. So this is a complex valued function from the space of metrized objects into C. Then the fourth part of the data is the mass functions. This is a function from the metrized object to this real valued function, which takes positive real values.
Wait, do you have a definition of what a metrized object is?
This data, so
What is H?
H is a Hermitian metric.
Category.
So this is just sorry, K linear, where K is either the field of complex numbers or from Archimedean field. And so if you want to have some category in mind, either you take this Fukaya category that Max was talking about, or the category of representation of a quiver, or category DB effects.
These are objects of the category.
E is an object, H is a metric on this object. Yeah, yeah. So I mean, so this is just a definition. I'll give an example in a second. So let's go over the data. And so then the F part is the flow. So this is one parameter group of continuous automorphisms. And so this automorphism, yeah, so I have a space, sorry, I have a space, and so it will be an example. So these are data, and then we'll try to, so what we are trying to do is try to produce a general approach that works for, well, maybe not all categories, but at least the categories that Max was discussing today. And then if you have this data, so the idea is that try to formulate a general statement that if you have a category which satisfies this data, then this categorical Kobayashi Kitchen corresponder holds. So the last part of the data is a pair of real functions, and so these are so-called amplitude plus and amplitude minus. So this, of course, measured on MET. Everything is on MET. So so we'll call chi Kobayashi Kitchen category if chi satisfies the following axioms. So axiom 1 is so-called, sorry, I made a mistake here, so BPS inequality. So the mass function, so on EH should be greater than the absolute value of the central charge. So it's mass here, not net. So the real value function S theta should be convex along the, defined as follows, should be convex along the geodesics for every theta. So the mass function extends on the compactification of this space MET. So the compactification hopefully will be done by adding the carbon-Racine filtration for the vigilant stability. And then the fourth axiom is that the mass decreases along the flow. So then these functions, the potential and the amplitude functions should have certain additivity property. So the scalar potential of the function S, when applied to objects, so I didn't write the matrix here, but so it's E in H1 and A in H2, and so the function is supposed to be additive on the metrized objects. And similarly here, the amplitudes, yeah, sorry, I apologize, it's direct sum of the form. And so it's amplitude of E direct sum F and minus of E direct sum F. And the last axiom is that there is a compatibility between all this data with the triangulated structure. In other words, there is certain rescaling, the flow that we have introduced, and also the shift in the category. So all these are supposed to be forming certain semi-group. So one can say precisely what this is, but so I won't go into these details now. So so let Chi be a Kobayashi-Hitchin category, a category which satisfies the 7 axioms. So then we say that E is theta polystable if this scalar potential attains a minimum on the subspace of MET consisting of objects with metrized objects with the following amplitudes. So, so we take a part of this metrized object, and so we restrict our scalar potential on it. And so once again, we claim that E is polystable if S that we defined as poles attains a minimum on this subspace. So similarly for semi-stable, we request that this function is bounded from below. So now the conjecture is that if we have a general category which is of this Kobayashi-Hitchin type, maybe satisfy all this. So it gets all this data and satisfy the 7 axioms. So if we restrict, so if we fix argument of the central charge theta, then x theta is denotes the subcategory of stable objects with slope theta. Then the category chi theta, and the central charge define the bridgeal instability condition. And so we say that the object E is Hermite-Einstein object of slope theta if it is a critical point of the S theta. So this is this real part defined as an imaginary real function defined as an imaginary part of E in power I theta times S. And so the categorical Kobayashi-Hitchin correspondence is that we have a homeomorphism between the modular space of bridgeal unstable objects and the modular space of Hermite-Einstein object for slope, both of them for slope theta. So, so these are the definitions, and so the conjecture is basically that if we have a general category which satisfies this Kobayashi-Hitchin data, then one can actually establish a correspondence between the algebraic part and the, this analysis part, and in such a way, this is like a categorical generalization of the Kobayashi-Hitchin correspondence. So now let me refer back to this example that Mark started discussing this morning. So the example is the example of a quiver. So we'll start with a quiver Q, and so V are the vertices and alpha are the arrows. So the objects of this category associated with the representation of the quiver are complexes E with so here J moves over Z, so this tells you how far do you go over the complex. And so D are the pieces of the differentials on each of these vector spaces. And so T alpha are the endomorphisms which move over from one vertex to another. So this linear algebra data describe the category of complexes associated with this quiver. And so the new thing which is in addition to something that you all know very well are this data of Hermitian metric associated with each of these vector spaces. So we put an Hermitian metric on this of these vector spaces, and then the pairs EH become metrized objects. So of course, in order to make this a category of representation of quiver, so we put this additional data that the square is equal to 0. And of course, the endomorphisms T alpha commute with the differential. So now, let's try to define the analogs of all this Kobayashi-Kitchen data in this category. So let's define an operator Z, which combines a complex value function with a projection on each of these parts of the complex. So we take ZB for a vertex, and then we project this to the corresponding piece of the objects, sorry, a piece of the complex. And so the sum of all these numbers defines an operator, which will denote by Z. And since we have a Hermitian metric, we can define the adjoint operator. So we defined P0 as a operator in the following way. So this is the commutator of the adjoint of the differential. So here is the differential, and this is just the adjoint with respect to this metric. And similarly, the operators T alpha are the adjoint operators with respect to this matrix of this operators T alpha.
Why should I not be bothered that this kind of depends on the choice of representative?
Yeah. So that's a good question. So indeed, so far everything depends on the choice of this structure.
No, not the choice. The choice of presentation as a complex. It's not. This is the space of metrics doesn't depend on the quasi-isomorphism class of the complex.
I mean, the way we set it, it does depend. Hopefully, one can show that it doesn't. So, in a way, the way things are defined now, it really depends on the setup. So now, let's define the mass function. So remember, this was part of the. So the mass function was supposed to be a real value function from met to R. So in this case, so this is the trace of the norm of Z plus P0 minus the so it's trace of the normal delta, sorry, no. So now the Kerr potential is also defined in terms of this operator Z and the trace of these operators which we have defined, T alpha and the differential, sorry, this should be T alpha dagger. And the flow is defined as follows. So let's define the operator of degree as a sum over all these vertices V. So I apologize, it should be V here, not J, of the projection of over V, projection over each of the pieces of this complex. And then D is a homomorphism from R to R. Let's say it's a maybe we require this to be a complex function. Sorry, about this. And then the flow is defined as the you apply this function to this operator. So the argument here is defined as a real part of Z over the square root of Z plus D0. So yeah, but so this is an operator. So Z plus B0 is an operator. So I take the real part over the norm of the operator. It's like X. Yeah. So it's the analog in complex numbers. So X over X squared plus Y squared, where this is the real part. So now I'm already with this definition, so it's quite a bit of a challenge to first check the some of this axiom. In particular, the BPS axiom is, let me remind you. So the BPS axiom was that the mass is greater than the absolute value of the central charge, and we're already checking this axiom is quite a bit of a challenge.
Inequality should be not strict.
I think should be strict. Sorry? The inequality, the BPS.
Oh, not strict.
Okay.
No,
Like for stable objects, it's equality.
Ah, yeah, okay, sorry. So, and once again, I want to emphasize here that the way all these things were defined here certainly depends on the choice of make some choices here, so certainly depends on the choice of T-structure for this category, so showing some independence of all these flows on net and so on from the choice of T-structure. It's quite a bit of a challenge too. So at the moment we don't know how to do that. So once again, this is just a program, but the idea is that that gives you a general approach to defining this modular spaces of objects on categories. So if it's possible to overcome all these difficulties, then so the only, well, not everything has been completely checked. Yeah, so certainly we believe that, at least in the case of Weaver, this Kobayashi-Kitchen correspondence would work, but not everything has been checked. So now, similarly, one can try to define the similar categories in the case of DBFX and in the case of that Maxime discussed. So these are these categories, the Schubert categories. But let's return to the case with which I have started. So this case is the derived category of coherent shifts on smooth projective variety, or if you like, on algebraic surfaces. Quite a bit of work in this direction actually has been done by Professor Yao and his team. And so in this case, one can define the central charge for the objects in the category to be the integral over this trace of in power I over h, which is the Planck constant, plus f being the corresponding curvature. So W is the carrier symplectic form. And so if you let h go to 0, you have this expansion, and so you more or less see that in the limit you get the stability conditions that you know from the classical story. And so this suggests that one should be able to define the intersection theory on these modular spaces of objects, which in limit should give you, in the case of algebraic surfaces, the classical intersection theory, which is nothing else but the so-called Donaldson invariance. So, and let me just briefly remind you that Donaldson invariants are defined by using the Chern classes by over the of the universal bundle over modular space of SU2 bundles times X. And so similarly, one should be able to define similar classes in this case, where mod is staying here for the modular space of objects, and instead of H2 as in the classical theory, we have the periodic cyclic homology associated with your category DBFX. And so hopefully at least up to dimension 3, one can try to find these modular spaces, and then this Donaldson invariance associated with these modular spaces. So now, as I said, one possible application of Donaldson invariance is to try to study semi-orthogonal decompositions of the category by this Donaldson invariance. So classically, what Donaldson has noticed is that the this rational surface, CP2 blown up at 9 points, is not homomorphic to Dolgachov surface X by comparing their polynomial Donaldson invariants. So as I mentioned, in the focus in the limit, you get this classical Donaldson invariance to be the limit of the categorical Donaldson invariance associated with these surfaces. And so, as we discussed at the beginning of the talk, when it comes to categories, the information would distinguish the derived category of P2 blown up at 9 points and derived category of the Dolgachov surfaces, this phantom category. So remember, this was a category which has trivial K theory and is non-trivial. So the question is, do categorical Donaldson invariants detect these phantoms? So once again, so let me just emphasize here that a phantom could appear in some semi-orthogonal decomposition, but it is not clear that it appears in all semi-orthogonal decomposition. So if the Donaldson invariant detect this phantom, so it will become an appearance of a phantom. It will become an invariant of the category. So if the answer is yes, then the next.
So it should be an invariant of the category.
Yes.
It should be independent of all this data that we have.
Well, I mean, it should be. I mean, it should appear for all semi-orthogonal decomposition. That's what. If the Donaldson polynomials take the phantom, then this is a semi-orthogonal decomposition is not an invariant. And Donaldson invariants are. So that's a way to encode information about the category in this Donaldson invariants associated with these moduli spaces. And so if this could be done, so the natural conjecture is that if you have a three-dimensional smooth projective variety, which has a phantom, it's a semi-orthogonal decomposition, then this manifold is not rational. So it's hard to make birational invariance from semi-orthogonal decomposition, but if these Donaldson invariants are definable, then it should be possible to make them categorical invariants. So at the beginning, I promised that there will be analog of this rational blow-downs and operations on four-dimensional manifolds, four-dimensional real manifolds. And so remember that operations that were producing interesting structure distinguished, smooth structure distinguished by Donaldson invariants were the rational blow-down. And in dimension 3, where there is still some hope to define Donaldson invariants categorically, the analog of this rational blow-downs can be defined as follows. So let's say that we have two smooth Fano manifolds which have Picard 1. Then the theorem says that I can start with this Fano x1, do a toric degeneration, then do several projections from this singular toric variety to another toric variety, and then regenerate back in order to obtain a new Fano x2. So, so this is something that I propose as an analog of this rational blow-downs in four-dimensional topology. And an actual question by analogy with what we have with in four-dimensional topology is try to compute how these categorical Donaldson invariants behave under these degenerations and projections. So if that is possible, then there will be a formula in the same way as in the four-dimensional topology, connecting the categorical Donaldson invariants of dB of x1 with the Donaldson invariants of dB of x2. And so this Donaldson invariants might actually be used to approach rather classical questions in algebraic geometry. So for quite some time there was a question, if you have an algebraic surface, can you split the transcendental chord structure on H2 of this algebraic surface over Z? So that was a question that was not known, but then on the first meaningful example, it actually happened that this is possible to do. Indeed, if you take the Fermat sextic in P3, you could split this chord structure over Z. Now, remember there was a theorem which Donaldson proved that for manifolds of simple type, the splittings of the corresponding manifolds are actually not quite easy to achieve due to some constraints from coming from Donaldson invariants. So it would be interesting to try to apply them in this categorical setting in comparison with this categorical structure. So if indeed you can show that there is no splitting of this form, this would have some interesting applications to rationality. So I mean, I have prepared some other things, but I guess I'll stop.
Questions?
Yeah, I see. What does multiplication be different?
I like to make correction on some of the terminology. In 1974, Yang published a paper on constructing an anti-Scherbium connection of four manifolds. Where he pointed out the anti-Scherbium connection is the Cauchy-Riemann equation. And in fact, he was the first one who constructed everything on this connection on a Taylor surface. So I think it's not right to call it everything Einstein, yes, we call everything Young.
Okay.
Because Yang was the first one.
Yeah, actually, Max complained already. So,
well, that's the first thing. The second thing, the conjecture which we call Kobayashi's teaching correspondency was actually a well-known folklore conjecture after I proved my Krabi conjecture. The difficult part was the proof, which takes me and Uhlenbeck and Brown a long time to accomplish. So I don't believe this should be called Kobayashi teaching correspondency. In physics community, we call it DUY correspondency or DUY beyond the Japanese field. Because the proof really is a non-trivial field, as difficult as the Krabi conjecture.
No, I wasn't aware of that. Thank you.
So, one important property of Donaldson invariant is invariant smooth. Do you expect that this time is smooth invariant?
No, obviously not, because already in higher dimensions it doesn't depend on.
I mean, but in the fourth dimension, and also in the sixth dimension, you ask if it is effective invariant.
Well, so this is, these Donaldson invariants are just with modular space of S with two bundles, and this is much more.
Yeah, I know, because that's why I'm saying.
I mean, it's quite possible that they are smooth invariants, all of them in dimension 4, but certainly that's not true in
Yeah,
higher
but you
dimensions.
can ask whether it is effective invariant.
Yeah.
So your formal manifolds have
plus equal to 1.
Or greater than.
So Donaldson invariance is sort of not quite straightforwardly invariant. So could you clarify that in light of your Katzarkov?
But wasn't there a paper of Tochik where he actually?
Maybe is there a canonical chamber for Kalin surfaces?
I think it does something. I think that indeed it was greater than 1. And then Kochik did write the paper when its equality was for symplectical. I mean, I could be wrong. So certainly there is no issue with B2 plus greater than 1.
Well, I mean, if you were doing Seiberg-Witten invariance that I know a bit more about, then with B plus equal to 1 in the symplectic form, you just take the Taub's chamber where you just use a term by a big multiple of the symplectic.
I see. So
it's canonical.
you don't want to use the Dons and Thomas equal to Seiberg-Witten because
So
this is precisely the point. But this is precisely the most difficult part. B2 plus equal to 1.
Well, of course, right. It's not a single invariant.
Any further questions? Thank you.